as we go into revisiting the second law of thermodynamics, in order to properly think about efficiency, we're going to have to think a little bit about the work being done by a gas. So I'm starting here as a bit of a prelude. So let's just say we got a cylinder, and let's lie it sideways so we don't have to think about gravity at all. If we go ahead and do some process where the gas expands, let's say that the cylinder as a result expands by some width delta x. Now, if we're not going too crazy about all this so that we can follow the quasi-static process assumption, the force exerted by the gas here will always be very close to the force being exerted by the air on the outside. So we can work out that the work done by the gas, so this is by, not to, or by, not on, will be the force exerted by the gas times the displacement, delta x, from the definition of work. But this force will be equal to the pressure times the area. And the area here times this displacement, that's going to correspond to this volume right here, delta V. So we can write that the work done by a gas, is P delta V. And so here I created an isobaric process, and we can go and look at a PV diagram for an isobaric process. So if in the example there we had a power stroke, so it was an expansion, so we would have started here and we would have finished there. And this area right here, well, this distance here is delta V. That height there is P. So this is P delta V right here. So the work done is equal to the area under the curve. Here the work being done by the gas will be positive if we're going right to left. And this is just, if you think about it, started with a smaller volume, ended up with a bigger volume. This is the piston head pushing out, being pushed out. And the work done by the gas will be negative if we're going from left to right on such a diagram. Left to right. What if the pressure isn't a constant? Well, it turns out that it'll still be the area under the curve. So let's say we have an isobaric expansion. So in an isobaric expansion, the pressure will drop. The work is still going to be equal to the area under the curve there. And you can argue this by the usual tricks, where you slice this up into a whole bunch of little thin segments, each of which is where the pressure is approximately constant. And then imagine the slices getting ever thinner and thinner until you're just left with the area under the curve. Okay, so we'll keep that in our back pocket while we go on to thinking about the second law. And the other thing I will need to introduce to complete to get into our discussion of the second law in Carnot engines is an adiabatic process. So this is one where there is no heat transferred. So the best example of one that I can think of is, say, something like, there we go. Let's say we have a piston here, but now This is a very well insulated. So this piston's made out of really good insulating material. So there's no way we can transfer any heat in or out. And then, so we've got some gas in here. And then we can control the pressure by having a stack of coins sitting on top of it. And very slowly, one by one, you take the coins off and let them settle. And you need to do that so that all times you can have a well-defined pressure and volume. If you don't, if you take too many off at once, it turns out that the pressure in one part of the gas won't quite be the same as the other part of the gas, at least for a little bit. So you need to do this very slowly so that it's well defined so we can actually draw a PV diagram for it. And when you do, it looks an awful lot like an isothermal process, but it's not. It'll become clearer when you see me draw the two processes together on the same diagram. So let's say for this example here where we had an isobaric expansion, the pressure will drop because it took coins off. That made the pressure lower. And the volume increased because the piston went up as a result. So we can start here and say go here. And like I said, it looks isothermal, but it's not. It goes as V to the negative gamma. And for an ideal gas, ideal monatomic gas, this is equal to 5/3, but it can have other values. So if it's isothermal, it would be V to the negative 1. Here it's to the negative 5/3. So the pressure is dropping more rapidly with volume than it would in an isothermal process. But one of the things that we're going to take advantage of here is we know that from the first law, delta E thermal equals Q plus W, where this is the work done on the gas. And we want here the work done by the gas. So this would be Q minus W gas. In an adiabatic process, the heat transfer is 0. So we get that delta E thermal will be equal to the negative of the work done by the gas. Alrighty. So with all of that in place, we can go ahead and start to revisit entropy. When people were first thinking about entropy, again, the idea, remember, was that we were looking for a variable that would increase with time in irreversible processes. And although they weren't able to define entropy directly, they could at least figure out what the change in entropy was. It took Boltzmann with his statistical formulation of S equals K log W, or omega, whichever you prefer, to have an absolute value for S. But they found that, say, for an isothermal process, it would work to say that the entropy was equal to the heat transfer over the temperature if this was an isothermal process. And we can even fudge this a bit. So this is more of an aside if you're just wanting to do rough and ready calculations. If the temperature doesn't change too much, you can fudge it by saying it's equal to Q over the average of the beginning and ending temperatures. But this only works for small changes in temperature. But we'll kind of use this in a bit as we develop our arguments. Okay. And so the other big deal, though, is, like I said, since we want entropy to be a number that was increasing as irreversible processes occurred, we needed the entropy to be what's called a state variable. And what that means is that it depends only on the initial and final states of the system. And this is due to the very practical reason that we can only draw PV diagrams for reversible processes, which, when we talked about this earlier, were processes that take literally forever to do, but they're the only ones that you can actually legit draw diagrams for. Engineers have a whole black art where they've figured out how to draw diagrams of reversible processes that always give them the right answer for processes that are actually irreversible. And I always stand in awe of them doing that. But the big deal here is that we can then say that delta S is equal to S final minus S initial. And we had seen that in an irreversible process, you went from a state that had a low configuration, low number of possibilities, so that meant that the entropy would be low, to a final state that had a greater number of equivalent possibilities, so that meant that the entropy would be higher. So our delta S is indeed positive. Okay, so we've already stated that for an isothermal process, delta S is equal to Q over T. And now we can go ahead and fudge it a bit, use the fudge thing a bit to help us work out what it would be for an adiabatic process. For an adiabatic process, we can argue that delta S would have to be 0. And this is because we could imagine taking zillions of small temperature steps, but for each one of them, the heat transfer is 0, right? And so using our fudged version of this, where delta S is Q over the average temperature between initial and final, I keep sticking in Q as 0 here, and delta S remains 0. And you have to go through a limiting argument of making your hypothetical steps ever smaller and smaller and smaller to show that it all works, but it does. So for an isothermal process, we have that delta S is Q over T. And for an adiabatic process, we have delta S is equal to 0. So then for any real world process, remember, for a real world process, when we attempt to draw a PV diagram for it, probably all we will ever be able to do is just draw an initial state and a final state, and basically put a big WTF in between the two because we don't know how they connect. You can't even draw a line. To be able to draw a line would mean that a reversible process was happening, but in real world processes, they're not reversible. So all you can do is draw the dot at the beginning and at the end. But all is not lost. We can still figure out the change in entropy, because since entropy is a state variable, it only depends on the initial and final configurations of the system. So what we can do is we can replace this WTF purely for the purposes of calculating the entropy with an isothermal process and an adiabatic one, because we know how to compute them both. So what you do is you just figure out where exactly the isotherm and the adiabat will intersect. And then for this bit here, so this is my isothermal process. So for here, this will be equal to the delta S will not be 0 for that leg. It will be equal to Q over T. And then for this leg here, delta S is 0. So then that means for the entire process going from here to there, the change in the entropy is just equal to Q over T for the isothermal leg of the two processes getting connected. All right, so now that we know how to connect these two processes, we can, and now they've got a little better sense of entropy, we can go and revisit that statement that said that we could not have a spontaneous heat transfer from cold to hot. So if you remember there, I'd said earlier that you cannot, that this is not a diagram. This is a diagram. Sure, you can draw it artistically, but it's physically illegal to draw. So now we can get into why that is. So here, when we are transferring the heat transfer in both cases here, if this is a spontaneous flow, Q hot has to equal Q cold has to equal Q. So we can calculate the change in entropy of the hot reservoir. This would be equal to, well, heat's being transferred in, so it'll be plus Q over T hot. And meanwhile, in the cold reservoir, since we're transferring heat out, there'll be minus Q over T cold. So the change in entropy of the system will be equal to the two entropy changes added together. So this will be Q over T hot minus Q over T cold. So this will be Q times 1 over T hot minus 1 over T cold. Well, T hot is going to be a bigger number. So its reciprocal will be a smaller number than the reciprocal for T cold. So that would be less than 0. And that is impossible because remember our statement of the second law of thermodynamics says that delta S has to be greater than or equal to 0 for any process. Okay. To then go and show why the Carnot cycle is the most efficient possible cycle, I need to show you another diagram. This is one called a TS diagram. So this is going to work probably like you think it would. Instead of P and V on the axes, it's T and S, where S is the entropy of the system. For an isothermal process, so say we have an isothermal expansion, the entropy would go up because we'd have more states available. The change in entropy here would be greater than 0. And since delta S is equal to Q over T for an isothermal process, Q will be equal to T delta S. So that means here that we'll have a positive heat transfer in this process that's equal to the area under the curve. Because again, height T, width delta S. So this is for constant T. And again, we got the same deal here. The heat will be positive, so transferred in if we're going left to right, and negative if the diagram goes right to left. So with that in place, we can think about how to do a Carnot cycle. So here was Carnot's thought on the matter. He realized that you have to connect a hot reservoir to a cold reservoir. And so we can imagine just trying to figure out what would be the way that we could get the most possible work out of the system. So let's make a TS diagram and start to think about it. Well, you want to, he reasoned that, and so we'll just say here, there's our two S's. So his reasoning goes like this. Let's think about the power stroke. The most efficient possible power stroke you could have would be an isothermal expansion. And this is because this would maximize the amount of heat per cycle that I could get out of the hot reservoir. This whole area right here would be my Q hot. He then also realized that when you then want to connect to the cold reservoir, you can't have any pussyfooting about it. You have to do an adiabatic process when you disconnect from the hot reservoir and connect to the cold reservoir. This turns out to be an adiabatic expansion. And the reason here is if it were literally anything else, the details of how the engine is built, mostly have to do with the volume, are going to limit what the maximum possible entropy could be. So if it were anything else, you would have to start coming down too early, and you would lose, say, this piece right here. You wouldn't be able to take as much heat out from the hot reservoir as you possibly could. Now, because you're trying to maximize work, when you do the return, you want to reject as little heat as possible to the cold reservoir. So, again, he reasoned that on the compression stroke, you want to be doing an isothermal compression. Oops. Sorry about that. Again, same reasoning. So this would be the heat that you reject to the cold reservoir, Q cold. And if it were literally anything else, since you can't get colder than the cold reservoir, you would have some chunk of the curve sitting too high, higher than it should, and that would mean that you'd be rejecting more heat to the cold reservoir. And then finally, to complete the cycle for exactly the same reasons as the adiabatic expansion, you have to complete it with an adiabatic compression. Again, otherwise you'd have to start coming over too early and you'd waste all this extra heat down to the cold reservoir. So the difference between the hot and the cold reservoir is this area I'm cross-hatching here in orange. This is the work that we are going to get out from the gas. It will be equal to Q hot minus Q cold by the first law, because since we returned back to where we started, we are back at the same temperature, so delta E therm is 0. And so that is as efficient as it can possibly be. Anything else would require that you either don't take enough heat out from the hot reservoir, or you don't take as much heat from the hot reservoir per cycle as you possibly could, or you reject too much heat to the cold reservoir than you possibly could. So this is the ideal. This is as good as it gets for an engine, and since every one of these legs is being drawn solid, this is a reversible engine. So that gets you your delta S equals 0. Any real world process will give you delta S greater than 0. So this is the only one. You can see right here, you loop back, you end back up at delta S equals it same S you had before, so delta S equaled 0. Second law of thermodynamics says delta S can't go negative, so this is literally as efficient as it gets. Now, we can imagine what this looks like if we draw a PV diagram for it. So for a PV diagram, it's going to look something kind of like this. You'll have your isothermal expansion here, and then, whoops, that's maybe a little too extreme. And then you'll have your adiabatic expansion here, whoops, followed by your isothermal compression here, and your adiabatic compression there. But we can work out what the efficiency of our Carnot engine is, because we know that over an entire cycle, delta S has to be equal to 0. Actually, let me draw that down here. Because anything less, you won't be as efficient. Or anything more, if delta S is greater than 0, you won't be as efficient. So this will be equal to, sorry, let me just start by observing. This will be equal to delta S for the isothermal expansion plus delta S for the adiabatic expansion plus delta S for the isothermal compression plus delta S for the adiabatic compression. The adiabats we already saw give us delta S's of 0, and we know that because this is an ideal engine, delta S is 0 for an entire cycle. So let's just put in 0 equals delta S for the isothermal expansion. That's on the hot side, so this is Q hot over T hot. That's 0. This will be minus, because it's an outbound flow, Q cold over T cold. So this gives me, for a Carnot cycle, Q hot over T hot would be equal to Q cold over T cold. Now, we can think about the efficiency here for a moment. And actually, let me rearrange this. Maybe more useful will be to say that Q cold over Q hot will equal T cold. Whoops. Equal T cold over T hot. All right. So now we can calculate our efficiency for our Carnot cycles. This is our maximum efficiency. Any efficiency is the work over Q hot, because this is what you paid, sorry, this is what you got, and this is what you had to pay. And this is equal to Q hot minus Q cold over Q hot. All right, so let's expand that out. Q hot over Q hot minus Q cold over Q hot. This is 1. This is 1. Now this Q cold over Q hot we worked out is also equal to T cold over T hot. So that is your maximum possible efficiency. It's 1 minus T cold over T hot. And this is because in order for it to be any more efficient than that, you would need the change in entropy of the working substance to go negative. And that would be a violation of the second law of thermodynamics. So that's why we can say, as an equivalent statement of the second law, that it is impossible to build a heat engine where the efficiency exceeds the Carnot efficiency. And similarly, to have a heat pump whose coefficient of performance is better than that of a Carnot heat pump. Alrighty, so that will do it, and I'll catch you in the next one. Have fun.